We turn to study chapter 3. Chapter 3 is about derivatives. Today, section 3.1, 3 topics. Topic 1, what is a derivative? Topic 2, a relation between derivative and tangent line. Topic 3, more examples about computing a derivative. Topic 1, you may have heard about derivatives. Then, what is a derivative? A derivative is a limit, a special limit. Given a function f and a point a on the x-axis, we compute this limit. Function minus function value at point a over x minus a. Now, let x approach the point a. Then this fraction will approach some number. Denote the number by L. Because a limit of this form has a lot of applications, we give this limit a special name and a special notation. The special name is, we call L the derivative of the function f at a point A. This is a popular name. A less popular name is, we call L the instantaneous rate of change of the function at the point A. The special notation is, instead of using L to denote this limit, we use f pi of a, namely f pi of a is this limit. This is the first formula to compute the derivative of the function f at the point a. We have a second formula. Make a change of the variable x. Let x be a plus h. A is a constant. H is a variable. Plug in a plus h in the x here. Then we have this equation. Now, simplify this limit. A plus h is approaching a. Then what number the variable h is approaching? Approaching 0. A plus h minus a is h. Then we have a second formula to compute derivative of the function f at the point a. The book calls this formula and this formula the definition of derivative of the function at the point a. Example 1. Consider this function. Find the derivative of the function at the point 1 and the derivative of the function at the point a. We have two formulas to compute a derivative. I am going to use this formula to compute derivative at 1. Then use this formula to compute the derivative at a. By formula, derivative at 1 is this limit. Plug in this polynomial in the function f and compute function value at 1. Then we have this equation. Function value at 1 is 0. To find this limit, direct substitution. Plug in 1 in x, But then we will have 0 over 0. We cannot tell the limit. To tell this limit, simplify the function by factorization. Factor the polynomial on the top, then we have this equation. Cancel x minus 1. Then we have this equation. Now, direct substitution again. Plug in 1 in x. Then this limit is this number. This number is 2. Therefore, the derivative of this polynomial f1 is equal to 2. Now, compute derivative at the point A. This time, I use the second formula to compute this derivative. By formula, derivative at the point A is this limit. Now, function value at A plus h. Function is here. Replace all the x by A plus h. Then function at A plus h is this expression. Function value at A. Replace all the x by A. Then function value at A is this expression. Now, to find this limit, we need to simplify the fraction. I first distribute this negative sign to the free terms to get this equation. Then I expand A plus h squared by this formula. Then I have this equation. Next, I distribute the number 3 to the free terms and the negative 4 to A and h. Then I have this equation. Now, in the numerator, there are many cancellations. We can cancel 1 and negative 1. We can cancel negative 4a and positive 4a. We can cancel 3 times a squared and negative 3 times a squared. After the cancellations, then we have this equation. We can further cancel h from the top and from the bottom. To see that, I factor h in the numerator out to get this equation. Now, cancel h, cancel h. Then we have this equation. In this limit, a is a constant. H is a variable. H is approaching 0. By direct substitution, plug in 0 in h, then the limit is this number. This number is 6a minus 4. About this example, there is a remark. In this example, we compute derivative at 1 and derivative at a separately. Actually, it is more efficient to compute derivative at a first. After we get derivative at a general point a, then set a to 1, we can get derivative at 1. In this way, we don't need to compute derivatives twice. Topic 2, a relation between derivative and tangent line. Consider a function f. Suppose the graph of the function is this blue curve. On the graph, there is a point P. The x-coordinate of the point is A. Because the point is on the graph of the function, y-coordinate is function value at A. Now, at the point P, there is a tangent line. And I want to find the slope of the tangent line. For the slope of a line, we have the slope formula. But this formula requires we know 2 points on the line. The difficulty of finding the slope of this tangent line is we know only 1 point on the tangent line, point P. We don't know a second point on the tangent line. To overcome this difficulty, we use a limit to find the slope of the tangent line. On the graph of the function, I pick a point Q. Suppose the x-coordinate of Q is x. Because Q is on the graph of the function, y-coordinate is function value at x. Now, join P and Q with a line. About this second line, I can write down its slope by the slope formula because I know 2 points on this line. I know P and I know Q. By the slope formula, the slope of the line PQ is y2 minus y1 over x2 minus x1. So I have this equation. Now I move x toward the point A. When x is getting closer and closer to the point A, Q is approaching P along the curve. Therefore, the secant line PQ is approaching the tangent line T. As a result, the slope of the line PQ is approaching the slope of the tangent line. So we have the slope of the tangent line is the limit of the slope of the line PQ as x approaches the point A. Now, plug in this fraction in MPQ, then we have this equation. So, the slope of the tangent line is this limit. But this limit is derivative of the function at the point A by definition. So this observation says that derivative of the function at the point A is the slope of the tangent line at the point A. I mark down this as fact number 1. Derivative of function f at the point A is the slope of the tangent line to the graph of the function at the point P. This point, x coordinate is A, y coordinate is function value at A. Now, I show you some examples about this fact. Example 1. The graph of the function g is this blue curve. Now the question is, arrange the following numbers in increasing order and explain your reasoning. We have 5 numbers. Some are derivatives. A derivative is a number because derivative is a limit. A limit is a number. According to this fact, derivative at -2 is the slope of the tangent line at -2. So at -2, I draw a tangent line to the blue curve. Then the slope of this tangent line is derivative at -2. Now, I guess the slope of this line is 1. So roughly, derivative at -2 is 1. Now, derivative at 0. According to this fact, this guy is the slope of the tangent line at 0. At 0, I draw a tangent line to the graph of the function. The slope of this tangent line looks like 0 because this tangent line is about horizontal. So I guess the derivative of g at 0 roughly is 0. Derivative at 2. This is the slope of the tangent line at a point 2. At a point 2, I draw a tangent line to the graph of the function. This tangent line, I guess, its slope is -1. So derivative at 2 roughly is -1. Now, this derivative at 4. According to this fact, derivative at 4 is the slope of the tangent line at 4. So I draw the tangent line at the point 4. Then take a guess on the slope of this line. My guess is about -0.5. Therefore, I have derivative of the function at 4 roughly is -0.5. Now, after I have this information, I can arrange these 5 numbers in increasing order. The smallest number is derivative at 2, -1. So derivative at 2, the smallest. The second smallest number is derivative at 4. It is -0.5. So second small number. And the third smallest number is derivative at 0. And then 0, this number, put this number here. The largest number is derivative at -2. It is about 1. So this is the answer to this example. Example 2. Let function f be x to the third, and p is a point on the graph of the function. The graph of this function is this blue curve. P is a point on the graph. Because this point is on the graph of this function, so the y coordinate is function value at the x coordinate. Plugging 1 in x, then 1 to the third is 1. So function value at 1 is 1. Part A. Use definition of derivative to find the slope of the tangent line to the graph of the function at the point P. At the point P, there is a tangent line. Definition of derivative means these two formulas. These two formulas says that a derivative is a limit. The book calls these two formulas the definition of derivative. B, after we find the slope of this tangent line, then determine an equation of the tangent line at the point P. Now, solution to part A. Let MT denote the slope of the tangent line at the point P. M means slope, T means tangent line. By fact number 1, the slope of the tangent line at the point P is equal to derivative of the function at the x coordinate of the point P. The x coordinate of this point is 1. So the slope of the tangent line at P is equal to derivative at 1. To find this limit, we have two formulas. Which formula is better? That depends on the function f. For the function x to the third, I choose the second formula to compute this derivative. By formula, this derivative is equal to this limit, where a is 1. A is 1. Now, to find function value at 1 plus h, replace all the x in this equation by 1 plus h. Then function value at 1 plus h is 1 plus h to the third. To find function value at 1, plug in 1 in x here. Then we get 1 to the third. So we have this equation. To find this limit, direct substitution, plug in 0 in h, but then we will have 0 over 0. We cannot tell the limit. To tell the limit, we need to simplify this fraction. How to simplify the fraction? I expand this power 1 plus h to the third by this formula. Then I have this equation. Now simplify the numerator. I can see that I can cancel 1. Then I have this equation. I can further cancel h from the top and from the bottom. To see that, I factor h in the numerator out to get this equation. Now cancel h, then I have this equation. Now for this limit, I plug in 0 in h, then this limit is equal to this number. This number is 3. So therefore, derivative of the function f1 is 3. And the number 3 is also the slope of this tangent line. Now, part B. Determine an equation of the tangent line at the point P. About this tangent line, now we know the slope of the line. The slope of the line is 3. And also we know one point on the line. The point is point P. So we can use point slope formula to write down the equation of the line. This is the point slope formula of a line. x1, y1 is the point P. So by this formula, y minus y1, y1 is 1, is equal to slope is 3. Parenthesis, x minus x1, x1 is 1. Simplify this equation, then we have this equation. This equation is the answer to part B. Example 3. consider this function. The graph of this function is this blue curve. The domain of the function is from negative 0.5 to positive infinity, including negative 0.5. For the numbers that are less than negative 0.5, this function is not computable. So from negative infinity to negative 0.5, this function has no graph there. Now, part A. Find derivative of the function at 0.4. B. Determine an equation of the tangent line to the graph of the function at point P. Point P, x coordinate is 4. Because y coordinate is function value at 4, so point P is on the graph of the function. Function value at 4 is 3. How to get the number 3? Plug in 4 in x here. Then the function value is 3. At point P, there is a tangent line. Now, part B. Write down the equation for this tangent line. Now, solution to part A. To find this derivative, we have two formulas. Each formula works. In this example, let me pick this formula to compute the derivative. By formula, we have this equation where A, the point A, is 4. Now, plug in square root of 2x plus 1 in function f here. Then we have this equation. The function value at 4 is number 3. So we have this equation. To find this limit, direct substitution. Plug in 4 in x. But then we have 0 over 0. We cannot tell what is 0 over 0. So to determine this limit, we need to simplify the function. Because the function contains a square root, I want to use algebraic conjugate to simplify the function. That is, I want to use this formula to simplify the function. I want to use the square here to cancel the square root. Now, consider the numerator as a minus b. Multiply the numerator by a plus b. Then multiply the denominator by the same thing, a plus b. This fraction is equal to 1. This guy divided by itself is 1. So actually, I just multiply the function by 1. I didn't change the function. A fraction times a fraction is numerator times numerator, numerator times numerator, and denominator times denominator. So we have this equation. Now, for the product in the numerator, I can apply this formula. A minus b times a plus b is a square minus b square. Cancel square root and square, then we have this equation. 1 minus 9 is negative a. We have this equation. Take out the number 2. we have this equation. Cancel x minus 4 from the top and from the bottom. Then we have this equation. Now, to find this limit, try direct substitution again. Plug in the number 4 in x. Then the limit is equal to this number. This number is 1/3. So derivative of the function at point 4 is 1/3. Part B. Determine an equation of the tangent line to the graph of the function at point P. That is, write down the equation of this tangent line. In part A, we have found derivative at 4 is 1/3. By fact number 1, derivative at 4 is the slope of the tangent line at the point P. The point P, x coordinate is 4. So about this tangent line, we know slope is 1/3. And also we know one point, the point P on the tangent line. So by point slope formula, we can write down the equation of the tangent line. By point slope formula, y minus y1, this is y1, is equal to slope 1/3, parenthesis x minus x1. x1 is 4. Function value at 4 is 3. So we have this equation. Simplify this equation, then this is the answer to part B. Topic 3, more examples. Example 1, under this topic. Consider this function. Find the derivative of the function at point 2. We have two formulas to compute the derivative. Both formulas work well for this function. Let me pick the second formula to compute the derivative. By this formula, we have this equation, where the point A is 2. Now, plug in 2 plus h in the x here. Then the function value at 2 plus h is this fraction. Plug in the number 2 in x. Then the function value at 2 is this number. Simplify this guy a little bit. We have this equation. Now, to find this limit, plug in 0 in h. But then we have 0/0. We cannot tell what is 0/0. So to find this limit, we need to simplify this function. Because the numerator is a fraction minus a fraction, I want to use common denominator to simplify the function. The denominator in the first term is h plus 3. And the denominator in the second term is 3. The common denominator is 3 times h plus 3. Now, I multiply the top and the bottom in the first term by the number 3. Multiply the top and the bottom in the second term by h plus 3. Then I have this equation. Now the two terms have the same denominator. So I can combine the two terms to get this equation. This function is a fraction divided by h. I can write this function as the fraction times 1 over h. Here is one example. 3 over 8 over 3. This fraction divided by 5. I can write this number as the fraction times 1 over 5. It is 8 over 15. You can have a check with your calculator. Compute this number, then compute this number and see whether or not they are equal. This is a fraction times a fraction. It is equal to the numerator times the numerator and denominator times denominator. So we have this equation. Remove the square brackets, then we have this equation. Now, distribute the negative sign here to h and to the number 3. Distribute the number 3 here to h and to 1. Then we have this equation. Now, cancel the number 3 and cancel 1h. Then we have this equation. Cancel h from the top and from the bottom. We have this equation. To find this limit, direct substitution. Plug in the number 0 in h. So the limit is this number. This number is 2 over 9. Therefore, derivative of this function upon 2 is 2 over 9. The second example. If the tangent line to the graph of the function f at the point 4, 3 passes through the point 0, 2, find the function value f4 and the derivative of the function f4. Here is a diagram about this example. The blue curve is the graph of the function f. The point 4, 3 is on the blue curve. At this point, there is a tangent line, and the tangent line passes through the point 0, 2. 0, 2 is here. Okay, now find the function value f4 and derivative f4. Because this point is on the graph of the function, the y coordinate is the function value at the x coordinate. The x coordinate is 4. So this number 3 is the function value f4. Therefore, we have f of 4 is equal to 3. Now, we turn to determine derivative f4. Derivative f4 by fact number 1, it is the slope of the tangent line at the point 4. That is, this guy is the slope of this tangent line. Now, about this tangent line, we can determine the slope because we have 2 points on the tangent line. 4, 3, 1 point. The second point is 0, 2. So by the slope formula, okay, the slope of the tangent line of this tangent line is equal to y2. I consider this point as y2. y2 minus y1 over x2. x2 is 0 minus x1. x1 is 4. Then the slope of the tangent line is 1/4. So this line, the slope is 1/4. So therefore, derivative f4 is equal to 1/4.